Everybody give a big wave to Graham, who's back. We're very excited to see him back and in good spirits. All right, let's look at our announcements for today. So, lab supply pickup today. DMart, did you want to say a word about that?
Sure. Hi, everybody. My name is Daniel Martin. I also go by DMart, he, him. I am the laboratory supervisor for the chemistry department, so I handle all the fun stuff you're going to be handling in lab. So today we're going to be distributing the supplies that you're going to need for tomorrow, as well as having lab notebooks available for those of you that need to purchase one. And that's going to be in the atrium. For those of you that don't know where the atrium is, if you go to main hall, it's just towards the river from main hall. And those are going to be the doors you want to enter. We'll have everything set out for you. If you need to purchase a lab notebook, you can either pay in cash. It's not actually Viking Gold, it's charging to your student account. And I'll have a sheet here that you can just fill out if you need to charge it to your student account. But yeah, I'm hoping we don't have to prop the door, because it seemed like some people were able to get in the building. Not propping the doors just because it's super cold out and I don't want to freeze in there. And Mike's going to be there with me this morning into the afternoon as well. So come by, get your stuff. For those of you who are isolating because of test results, we will handle you separately. Get a hold of Mike with those sorts of questions.
And I saw someone from physics in the atrium too, handing out kits. So you just should wave at the window. If you can't get in, someone will see you. We will let you in. Question from Joy.
Sorry, I can't remember if we still have 50-page laboratory notebook, or are they only for 100-page notebook?
We do have a few of the 50-page left. Those are $10. The 100 pages are $13. I'm transitioning to just offering the 100-page just because of the very small price difference from that. But yes, I do have a few of those left over that I would have put on the cart.
Get them while they're hot. 50-page lab notebooks. All right, excellent. Let's see what else we've got here. So pick up your lab supplies today and purchase a lab notebook if you need one. Open hours assignment. Remember to come to open hours. You can come to mine, you can come to Graham's, you can come to Mike's. Please come on Zoom. We are not technically supposed to be seeing students in person yet. And there are still, I believe, 39 of you who need to come to office hours this week. So come early if you can, so that we're not totally inundated. And then the final announcement is about drop-in tutoring. Perla Vieira is here to give a plug about that.
Hello, everyone. I'm sorry my camera doesn't work today, so you can put a face on my name if you don't know me. I'm the president for the American Chemical Society here at Lawrence, and we host every single week on Thursday at 6:30 p.m. like a tutoring section for anyone in general chemistry. It's free. You don't have to do anything. You just come in, ask your questions, and you can leave. Or if you want to use homework with us, then you can do that. We don't mind. And I think Rachel left the Zoom link on Yes Campus site. So please go to that one. Don't go to the lecture one, because I won't know if you need help, because I'm not going to pop it in there. Okay. And I usually don't answer emails because I don't like emailing tutoring sections or anything. So I'm going to drop out my email anyway and my phone number in case you need to text me at 11 p.m. because I do answer. I'm very nice on that. And we also have meetings for Axel every Wednesday. I will send an email later today about something special this week. So that's all I have to say. Is there anything else I have to cover up?
Nope, just the tutoring session on Thursday exists. It's right before your homework is due every week. So it's a great opportunity to meet upperclassmen, get some help on your homework, maybe even meet some people from your class. And it'll be on Zoom. for this week until we come back.
Yeah, cool. Okay, I had to go to class now. Bye.
Thanks, Perla. All right, any other announcements, Mike or Graham, anything we need to say?
Yeah, just super briefly, a reminder to everyone that the spring term wait list is now open. So for those of you who were trying to get into 116 and couldn't, if there are any of you, that might be relevant to you or any other classes.
Yeah, so if you're taking 116, register for 116 so we know that you're going to be in it.
Even if you can only be on the wait list, we'd like to be able to see what the situation is ahead of time.
All right, good stuff. If you got questions, throw them in the chat. Otherwise, we are going to go ahead and start with our warm-up activity. Show you what we're doing today. You will find this on the Canvas page under Monday the 10th. What we're going to be doing is very similar to what we've done the rest of the week, last week. Here is your breakout room assignment. Find yourself. It is the same place that you were all of last week. Today, we're going to be reviewing chemical symbols. So on each of the slides, you are going to see 3 chemical symbols in 3 different boxes. So you and your team are going to figure out how many protons, neutrons, and electrons each of them has. And then you'll find the proton to neutron to proton ratio and write those down. And then if you have time, do a rough sketch of each of the nuclides in the box. I've already made the neutron, electron, and proton symbols for you. You can just copy and paste them and draw some circles. Please make sure there is a lot to do. If you're going to divide and conquer, talk to your group first. This is a group activity. Talk to each other, make the plan, make sure that everybody feels included and understands what is happening. All right. Breakout rooms. I'm going to give you 5 minutes. I'm going to make you self-sort because that's the lay of the land when there are 45 students. Here we are. Go forth. See you in 5.
Sorry, that was just that message that I had sent you.
Oh, excellent. Yes, thanks for the reminder. I totally did forget to do that. Let's try that again. So for the recording, here's the positron emission. Here is electron capture, and notice that the same process is happening here. Both of these involve a proton turning to a neutron. It's just a matter of whether something is absorbed or whether something is emitted on the way to making that happen. All right, and then there's one more process that we'll talk about, and that's X gamma ray emission. Gotta practice my Greek letters here. And a gamma ray is even more energetic than an X-ray. And this happens when you have some sort of an excited high energy nuclide, and it's in an excited state. And so we represent the excited state with this symbol. The horizontal, 2 horizontal lines through a vertical line, we call that the double dagger. That indicates that the nuclide is unstable because of its high energy status. More on that in organic chemistry with Steph. So after we finish some sort of a decay process and we're left with a high energy nuclide, that nuclide needs to relax down to the ground state, and it does that by emitting the extra energy as a gamma ray. So you often see the gamma ray emission as sort of a secondary step or part of another step, relaxing some daughter nuclide to the relaxed version.
We actually have gamma ray emitters here at Lawrence in the physics department. We use them for a kind of spectroscopy called Mossbauer spectroscopy, and they're pretty cool. Don't touch them though.
Yeah, you don't want to put your body in the direct path of that sort of beam. That's no good. Yeah,
I've handled a gamma ray source with my hands before. I had to screw it onto an emitter. It was the most nerve-wracking day of my life.
Yeah, gamma rays are so powerful that they can The gamma rays emitted from the sun can get to you even in the basement. They can pass through several layers of cement and still be detected in the basement. So gamma rays, so fun. All right, so let's go back to this picture of the valley of stability that we had from last time. You probably have this in the last page of your notes. So thinking about all those different types of processes that we just learned about, let's think about sort of all these different nuclides we have that aren't on the valley of stability, all these ones in the yellow area. Could we predict which one of those types of processes might happen? So we can predict based on this ratio that I had you find in the warm-up. So that ratio of the number of neutrons to the number of protons. If it's too large, it'll be one of the ones on this side. And if it's too small, it'll be one of the nuclides on this side. So if we think about the sorts of nuclides that might be like right here, that are above the valley of stability, we would say those have too many neutrons, right there. Their N to Z ratio is too large. And so one of those types of processes that we just learned about involved getting rid of a neutron, right? It involved turning a neutron into a proton. That was beta decay. So if the N to Z ratio is too high and we have too many neutrons to be stable, beta decay is what often happens. So for something over here like this. What if we had something on the underside, something where the N to Z ratio was too small, where the slope was lower? That means the nucleus has too many protons to be stable. The denominator of that ratio is too large. Well, one or actually two of those reactions that we looked at involve taking a proton and transforming it into a neutron, but the one that involved emitting a particle was the positron decay. So if you have a nuclide that's down here in this part of the graph, you might see it going through positron decay. And for these guys that are way up here in the super heavy part of the table, they just have too much mass altogether to be stable. There's too many protons and neutrons all shoved into one very, very small space. And so we'd like to get rid of as many protons and neutrons as we can at a time. And so our best option would be alpha decay. And I say best option not because the nuclide is making a choice, right? I don't mean to anthropomorphize it. This is the most statistically probable decay process to occur, is an alpha decay. So do I expect you to be able to say from any given nuclide what process would happen? No, but if I gave you some information, if I described a nuclide and I told you about what element it was, if I told you about the ratio, if I maybe indicated its position on the valley of stability, maybe you could make a guess as to which type of decay would be most likely for that kind of particle. All right, let's go back. We got a little bit of space left. The final thing I wanted to say about nuclear chemistry before we move on is that nuclear chemistry is something that happens naturally, and it also happens artificially. This is one of the most impressive areas of science that humans have contributed to, is there are some elements of the periodic table that do not actually exist naturally. They have only been created in the lab. So transmutations, that means that one nuclide is becoming another one. All the equations we've written so far have been transmutations. These transmutations can occur naturally or artificially. And I know nuclear chemistry can get a bad rap, right? A lot of dangerous, destructive things have come from nuclear chemistry. We've had wars based entirely around nuclear weapons, but there are also a lot of positive contributions to society that nuclear chemistry gives us. And I'll bet you know what some of them are. So go to the chat, tell me in the chat one thing that nuclear chemistry is used for that's a positive contribution to society. Let's see how many we can get. Cancer therapy, good. Smoke detectors, x-rays, right? Not that we really love airport x-ray machines, but they are useful. nuclear power plants, right? Let's see, I've also got on my list carbon dating. Remember, like Mike talked about last time, we can learn how many thousands of years ago particular important things in the earth happened. We've got positron emission topography, food preservation, lots of good stuff. And so finally, here's a picture of a PET scan. Remember we said that was positron emission. You might have had a relative that had to have a PET scan before in the hospital. So tomography means, I think, that we're making a map out of what we get. So basically what happens here is that some sort of a radioactive material, I think radioactive fluoride, you consume that in the form of a glucose drink or something, and it produces those positrons in your body. The positron finds a free electron in your body and annihilates it. That is the actual scientific term. The positron annihilates the electron and a huge amount of radiation is emitted. And then the 360-degree detector that you are sitting inside will detect that radiation, and you can use it to make a map like this one here in the bottom right. And this is especially used for detecting cancer or tumors in your body, because this process happens most often in the most active parts of your body. So it usually lights up your brain. It often lights up your digestive system, but it will also light up places like this that could be potential tumors. So it's sometimes necessary to pair it with other types of tomography like CAT scan or an MRI, but being radioactive for a couple of minutes can be really useful for detecting things that we can't actually see inside your body. We'll even remember to record this time. Okay, so we've been focusing in on one single atom and the different parts of inside of the different atoms. But in order for you to do things in the laboratory, you're going to need to do things with multiple atoms. So for Mike, we're going to take a sidebar and cover moles and talk about how to measure number of moles of something. So a mole is essentially like a dozen. It's a way of measuring a large number of atoms at a time. Atoms are very, very small, and we can't actually see them. There are millions of atoms or molecules in a single spoonful. And we can't actually see the atom. So it's not as if we could count every atom in a spoonful and tell us about how there were 10 times 10 to the 35th atoms there. We need some other unit of measuring them. We need to be able to measure those atoms, and the unit we're going to use to measure them needs to be much larger than a dozen, because there are billions and trillions of molecules just in a small volume. So we need a quantity much larger than a dozen. But it works the same way. So if we say we have a dozen of something, we're meaning that we have 12 of those things. And so the mole is the chemist's dozen. It's just a lot bigger. So a mole is 6.022 times 10 to the 23rd things, which is a number so large it would take your entire lifetime to count all the way up to that number. And so this number was chosen on purpose because it's the number of atoms that is in 12 grams of carbon-12. And this number is so important to chemists that we called it the mole, and we also call it by the name of the person who came up with this number, and his name was Avogadro. This is also called Avogadro's number. And it has its own symbol, and the symbol is a capital N for number with a subscript capital A for Avogadro. Oh, Mike has a little mole, little stuffed mole. Yeah, we're kind of obsessed with moles here. Yeah, look at all the zeros on that number. It's a big, long number that would take a very long time to count to. So let's just take a moment and appreciate how large a number 10 to the 23rd is. So how big is this number? So picture that you had like a spoonful of water. That's what that's supposed to be. Okay, so this is 1 mole of water molecules would be about 18 grams. So it would be about 1 spoonful. So if 1 spoonful has 1 mole of water molecules, let's compare that to the size of the Earth's population. So if we took those 6 times 10 to the 23rd molecules and we distributed them evenly between the 7.8 billion people, how many would each person have left? Each of the 7.8 billion people would receive 70 trillion water molecules. So Avogadro's number is like 7.8 billion times 70 trillion. That's how big this number is. It's unfathomably large. And that's how many molecules are in just 1 scoop of water. Can you imagine how many are in a gallon of water or a swimming pool of water? It's just unfathomably large. So we need to have this big unit to use to count them. And as you might have reached the conclusion for, a mole is just a number of things. And so depending on what that thing is going to have a different weight. It's going to have a different mass because every element has a different mass, every compound has a different mass. And so we need a new measurement to tell us how heavy a mole of something would be. So the mass of 1 mole of atoms or molecules depends on what elements are in it. There is not just one mass. There is a different mass for every item. And so we name that the molar mass. Logical. My favorite kind of name. And when I write it in my notes, I usually write it like this, as a double capital M for molar mass, and the unit is usually in grams per mole. So the number of grams or the mass that 1 mole of that item takes up. And so you can find the molar mass in our favorite place. In every square of the periodic table, the molar mass for that element is listed. It's right here. And I know that look you're giving me right now. Rachel, you're saying to yourself, we just used that number on last week. We said that was the atomic mass and atomic mass units. That was the mass of a single atom. And I am here to tell you that when Avogadro came up with this number, he was being really sneaky because this number is actually used for both of those purposes. That's the reason that he defined this unit the way it is, because this number represents the atomic mass and it represents the molar mass. If we think of it as the atomic mass, we're thinking of the mass of 1 atom in atomic mass units. So for example, for carbon, 12.011 atomic mass units is the mass of 1 carbon-12 atom. And if we thought of the number as the molar mass, it would be 12.011 grams in 1 mole of carbon. So that number actually represents both a micro scale number and a macro scale number. Molar mass in grams per mole is the same number as the atomic mass in atomic mass units. You'll notice that the 6.022 times 10 to the 23rd was also in the definition of atomic mass units from a couple of days ago. So the mole is really useful. It's a really useful way of counting how many particles we have, and it's a really useful way of weighing how many particles we have. And so now this is a new conversion factor that we can use to do math. And Aiden has a question. What's up, Aiden?
Can you go over one more time for the one problem you did where you got 70 trillion molecules. Can you explain the process of that again?
Yes, so what I did here is I took this number, the number of things in 1 mole, 10 to the 23rd, and I divided it by 7.8 billion, and I got 70 trillion. So if I took all of the molecules in a mole and I divided them equally between the 7.8 billion people on the Earth, each person would receive 70 trillion molecules. So it's a way of understanding how large the number is. The Avogadro's number is like 70 trillion times 7.8 billion.
All right, thank you.
Okay, other questions while we're here? Able to see everybody's faces while staring at the piece of paper. Okay, happy? We're ready to do some math? You guys practiced dimensional analysis for me last week, watching that pre-lecture video, working through it on the homework and working through it on the quiz. So now let's do some of that together. So now that we have the mole, we can convert between the mass of something, the number of moles of something, and the number of things of something that we have. The mole is going to be our key to connecting a feature that we can actually measure in the macro scale and our micro scale measurement of how many particles we're working with. And so to convert between each of these two, we have a different unit conversion factor. So to convert between mass and moles, we'll use our molar mass. That was that number that we got from the table in grams per mole. And if we want to convert between number of moles and number of things, we'll use Avogadro's number. We represented that by Na. And that one has a unit of per mole, or 1/mole. If you were counting pigs, this would be number of pigs per mole. If you were counting number of carbons, it would be number of carbons per mole. The generic unit is number of moles. And let's be a little more specific about what sorts of things we could count. So we could count anything we want, but in chemistry, we're usually counting atoms, or we're counting molecules, or we're counting ions, or we're counting formula units. Now, formula unit is the ionic version of a molecule. You don't, like a sodium chloride, you don't actually have a molecule of a sodium chloride, you have a formula unit, 1 sodium and 1 chlorine. So let's do a practice one. So let's say that we're living in the macro scale, as we do on a daily basis. We measure 2.5 grams of aluminum, which is probably like aluminum foil ball about that size. How many atoms are in something of that size? So remember, we can use these steps as sort of a map to plan this out. We're starting here in grams. We want to end over here in things. How many things? So we need to use 1, 2 dimensional analysis terms to help us get there. So we always start with the information we're given, especially if it only has 1 unit and we're trying to end with 1 unit. But now when we do dimensional analysis, we're not only going to include the unit grams, we're also going to include the unit of the molecular formula, because we might need to count grams of different types of things. So it is not just 2.5 grams, it is 2.5 grams of aluminum. So I'm going to use the molar mass to get from grams to moles, but if I write grams over moles, my dimensional analysis doesn't work, right? I need to have the grams part on the bottom so that the grams of aluminum cancels. So we're going to put moles on the top of aluminum and grams of aluminum on the bottom. 1 mole is going to have some number of grams. Let's look at our table here. Here's mine. I don't know if you can read it, but yours will probably look like this. Here's aluminum, and the number underneath the word aluminum is 26.98. So 26.98 grams per mole is our molar mass of elemental aluminum. So grams of aluminum cancels with grams of aluminum. Now we have moles, but we want to have atoms. So we need to use Avogadro's number. Convert, and Avogadro's number is things per mole. So we'll put moles on the bottom. And we'll put Avogadro's number on the top. 6 times 10 to the 23rd atoms of aluminum per 1 mole of aluminum. So our moles of aluminum cancels, and we have the unit we're looking for on the top. So this is where you use your calculator. I did mine already. Hopefully, if you do yours, you end up with the same thing as me. 5.6 10 to the 22nd. And we'll include our unit, atoms of aluminum. And if I think about the scale of the answer I got, if that seems like a reasonable number, I remember that Avogadro's number, 6 times 10 to the 23rd of water, was about 1 spoonful. This feels like a little bit less than a spoonful, and so that number is a little bit smaller. So that feels sort of on par, like the kind of answer I would have expected to get. Okay, questions on this? Okay. I cheated and I wrote the next question in advance, so you can write it down on your own or take a screenshot. We're going to do the same thing, but this time we're going to do it for a compound that has more than 1 atom in it. And so that's going to add an extra step of figuring out the molar mass of something that isn't listed on the periodic table. We couldn't possibly list the molar mass of every single compound that ever existed, or the periodic table would be 17 miles long. That's why we have the periodic table. We have the information for each of these different atoms, and we can use that to find the whole compound. So we'll find molecules first, and then after we do that, we'll count the number of carbon atoms specifically. So we're starting here again with mass, and to get the number of molecules, we need to go to the number of moles with the molar mass, and to the number of things with Avogadro's number. So let's get set up here. 70.2 grams of glucose. Somebody have a question? I heard somebody unmute. Okay, we'll keep going then. So we have grams. We're going to flip our molar mass upside down like we did before to get to moles. So 1 mole per some number of grams. And I don't know what that number is, but I'm kind of on a roll here. So I like to just leave a blank and come back to that and get my dimensional analysis all set up first. So I'll use the molar mass, whatever it is, to get to moles. Then I'm going to use Avogadro's number to get to number of molecules. So 6.022 10 to the 23rd molecules. And be careful not to abbreviate the word molecules as MOLS, or it's going to look like you've written moles. Just an unfortunate naming convention there. All right, so moles cancel, and we're left with molecules. So now we need to go back and figure out what the heck this number is supposed to be. And so what we're going to do is we're going to count up the molar mass of 6 carbons plus the molar mass of 12 hydrogens plus the molar mass of 6 oxygens. And so this is a weighted sum, kind of like we did for isotopes last week. So we need to go to the table and find the molar mass of carbon. Carbon lives here. You probably can't read it, but it says 12.0107. So we take the molar mass of carbon in grams per mole, and we multiply that by 6 carbons. Then we need the molar mass of hydrogen, which is way over here in the corner, 1.00794. There's no way you can read that. You believe me, right? You believe that I can read off of a table? You can always check if you don't believe me. All right, hydrogen times there are 12 hydrogens. And then we need oxygen. which is here, 15.9994. Grams per mole times 6 oxygens. So add that up on our calculator. Hopefully you got 180.156. I always carry as many significant figures at this point as I can get. And then I'm going to be lazy and I'm just going to draw an arrow to where that number needs to go. So 70.2 divided by 180.156 times 6.022 times 10 to the 23rd. We calculate that, so that should give us 2.35 times 10 to the 23rd molecules. That. Okay, so then we got one more step here for step B. So if we know how many molecules of glucose, how can we figure out how many carbon atoms there
I have
are?
a question really quick.
Yes, what's the question?
Okay, so you wrote 180.156 grams per mole, but
Mhm.
then in the denominator of the second term of it's just grams. Which one is it?
It's 180. I was just being lazy. So the 180 goes right here.
But is it grams per mole or is it just grams?
So it's 180.156 grams per 1 mole. So I've just written this number upside down. So the 180 grams is on the bottom and the 1 mole
Oh,
is on top.
okay. Okay, that makes sense. Thank you.
Yes, sorry. I was being lazy and not drawing the number in the right place. So we've taken the inverse of that number is right here. Good question. We always want to align that term in a way that causes the units to cancel. Okay, so our last step, we have this many molecules and we want to figure out how many carbons there are. There's one last type of tool we can use, and that is the molecular formula itself. We know that for every 1 molecule of glucose, there are 6 atoms of carbon, right? That's how we figured out what the molar mass was. And so we can use that to turn the number of molecules into the number of atoms of one particular thing. And this step seems to be particularly tricky for students, so make sure you pay attention on this part. So if we have this many molecules, the ratio we're going to use to convert from molecules to carbon atoms is we're going to say for every 1 molecule of glucose that I have, which is C6H12O6, there are going to be 6 carbon atoms. I could have set this up if I wanted to convert hydrogen. I could have said 12 hydrogens per 1 molecule, or I could have done oxygen, 6 oxygen atoms per molecule. I'm literally using the formula as my tool as a conversion factor. And so we can multiply that through, cancel our units, we end up with 1.41 10 to the 24th atoms of carbon. All right, questions on this? All right, everybody's happy temporarily. So we've got one more Chem 101 exercise for you. There we go, it started, so go ahead and